So in this video, I want to go through what's called Diels-Alder regioselectivity, or regioisomerism. So let me first just get into this term regioisomers. There is some question as to whether or not this is a real word. I'm going to lean towards yes, but let's just acknowledge that some people don't like the term. But regioisomers are isomers. That is, they have the same molecular formula, same number of elements, that sort of thing, but there's something different about the structures. But here, these are isomers resulting from reactions of different parts of a molecule. It's kind of a hard definition because there's also like site isomers, but this will work for now. Hopefully this will make sense in just a second. So regioisomers. Now, here's the issue. If I have a diene with like our two methyl groups plus a dienophile with, let's put some chlorine atoms instead of continuing to write the word stuff, and we do an endo reaction. The endo rule, the endo, a DA with endo selectivity. The endo rule refers to the relative stereochemical outcome. And we say that this reaction has stereo selectivity. It prefers to form one diastereomer over the other. But what's interesting about this is we have dienes and dienophiles that are both symmetric. I've been careful about choosing examples of Diels-Alder reactions because there's something that arises when both the diene and the dienophile do not have selectivity. Sorry, ran out of pages there. So I would say here that here they both don't have selectivity. Both my diene and my dienophile no longer have selectivity, jeepers, symmetry, excuse me. Now what that means is I could draw another Diels-Alder reaction and I could still maintain the endo rule where I select for the formation of a stereoisomer following endo orientation. So I would have this plus its enantiomer, where they're both wedges. Both of those are endo products. I'm just flipping everything. But here's the issue. Since both the diene and the dienophile do not have symmetry, there's another product that could form. I could form a product where I flip either the diene or the dienophile. In this case, I'm going to rotate this. And I could still follow the endo rule. And in this case, I would just have the chlorine on a different part of the resulting product. So these two structures, I wish I wasn't on separate pages, these two structures are regioisomers. They result from the same type of reaction at different, with different arrangements of starting materials, or different parts of the starting materials are reacting. Gosh, such a slippery slope with some of these definitions. The point that I want you to take away from this is you need to take a second and look. Is my diene and my dienophile, do they both have, are they both lacking symmetry? If they're both lacking symmetry, then you have to pay attention that we could have two approaches, that the two endo approaches for the dienophile. It could attack so the chlorine is close to the methyl group, or it could attack so that it's away from the methyl group. And this only occurs when both the diene and the dienophile are lacking symmetry. Okay, so let's look at another example. Let's say we take, this molecule and we react it with our chlorine atom, or chlorinated ethene. Here's another example. This molecule, while it has two methyl groups, we would say it has no symmetry. Okay, that's nothing we have to fret about. It's all about having both the diene and the dienophile lacking symmetry. But if you look, the monochlorinated ethene also has no symmetry. So what that means is we have two endo Diels Alder products. And for each case, we have their enantiomers. Now what this looks like is we're going to have an example where, gosh, sorry, I'm going to just make a bunch of pages quick. Where we could have, this one now is Z and a Z alkene and an E alkene, which matches here and here. And we could have our endo product where the chlorine comes in underneath and it's on the same side as the Z alkene. And that would give rise to this product following our general stereochemical model. I'm not showing the unfolding approach. I want to focus on the formation of multiple products. And if we consider a similar perspective, not chlorine, methyl. If we consider a similar perspective where the chlorine is facing down, or facing the closer to the E alkene in this case, we get a different product, a product that's not a stereoisomer. Remember, the wedge and dash choice is determined by the endo rule at the dienophile and by the inherent properties of the orbitals on the diene. So we have these two products, and these two products would be regioisomers. Isomers due to different regions of the molecules interacting with each other as a result of the same reaction. Now I have to emphasize, this is only an issue if both the diene and the dienophile lack symmetry. If one of them has symmetry, it only takes one, then we don't have to worry about this anymore. Let's go ahead and go back to this, and we're going to react this with chlorine atoms at both positions. Now we have symmetry. We have a bilateral plane of symmetry passing right through the molecule, which means if we follow the endo rule and use our general stereochemical model, the chlorines are going to face down, and we're going to have a methyl group as a wedge plus a dash. We still have to kind of recall that both enantiomers are going to form. But it wouldn't matter if how we rotate the dienophile, because it has symmetry. Okay, because it has symmetry, it doesn't matter which way I pick to orient them. If they both lack symmetry, then I have to consider both kind of arrangements. I usually pick the dienophile to interact, but I could rotate the diene and keep the dienophile still. I just don't want to rotate both, because then I get the same answer as what I started with, or an enantiomer of at the very least. Let's look at another example of something that's kind of interesting. We should first realize that the so this is kind of changing topics a little bit, but I'll relate it back. I just want us to realize or recognize that dienes could be drawn differently. And I want to make sure I touched on this, and we'll keep this in the context of regioisomers. So let's say I hand you these two molecules, and I say Diels-Alder reaction. At first, you might be like, well, how do I solve this? My diene doesn't look like a normal diene. What do I do? Well, let's redraw our diene with the S trans as an S-trans conformation. So redraw diene with the S-trans conformation. Okay, what does that look like? Well, I'm just going to draw the diene as I usually see it. And I have to recognize that the alkenes in my starting depiction of the diene were both E, and I have to add the methyl groups so that they're both E. Now, as a result, the molecules where I've highlighted the diene in green are now the same. These two structures are the same. So when I add that to my dienophile, I will get a Diels-Alder product. Now, what I meant to do was pick a symmetric diene just to illustrate that if the diene is also symmetric, we've seen this example before, actually. If the diene is symmetric, we also don't have to worry about regioisomers. But let's pick a symmetric diene reacting with a non-symmetric dienophile. Let's go ahead and look at that example. Okay, so I'm going to consider my diene like this. Okay, let's go ahead and try this reaction, and we'll say Diels-Alder reaction, and I'm going to follow the endo rule. Question: what does that look like? Well, let's first recognize that we have this diene here that I'm highlighting in green, so I could redraw the diene down here in an arrangement that looks more comfortable to me. That's reacting with a dienophile, the carbonyl attached to it, and it's the dienophile. I'll highlight that in red just so we can see. I know there's another double bond, but that's a double bond on an oxygen. And we're not doing heteroatom Diels-Alder reactions in this class. Now, I have to go back to my starting depiction and consider that both of these are Z or cis. So when I add the methyl groups, I have to make sure they're both Z or cis. In this case, they're pointing inwards. Now, doing a Diels-Alder reaction and applying the endo rule and my general stereochemical model, I can take this structure without stereochemistry and add wedges and dashes to it. But before I do, let me recognize that we have symmetry here. And if I have symmetry in either one of my diene or my dienophile, I don't have to worry about regioisomers. Okay, so what that means is that it doesn't matter that I don't have symmetry in my dienophile. I will just get one regioisomer along with its enantiomer. And so let's apply our stereochemical model to this. In this case, the methyl groups are going to be wedges. And the carbonyl, if following the endo rule, is going to be a dash. Okay, so that will do it for the Diels-Alder reaction. We looked at several types of approaches to solving Diels-Alder reactions in terms of their stereochemistry and regioselectivity, that is, which regioisomer was preferentially formed. We tried to rationalize the reasons why our single stereoisomer was observed along with its enantiomer. I should just get in the habit. I'm just going to go ahead and write this. I mean, honestly, it's great if you know that, like, when it's meso, you don't have to write plus enantiomer, but if you forget and you just write plus enantiomer in every case, that's okay. I'm not going to, this isn't the meso section of organic chemistry. That was back in organic 1, and I know it trips people up sometimes. So don't lose sleep over that. Okay, so we can put all of this together and predict a bunch of fun Diels-Alder reactions. One last, I should just mention one example. I know everybody wants me to be done with the module. Let's, Diels-Alder reactions can happen with alkynes too. It's not a big deal. And that makes, that adds another double bond, but deletes stereochemistry. So I'm just going to mention this quickly. If I replace my dienophile with an alkyne, okay, and we can add chlorines here. I like the habit of chlorines. This can also undergo a Diels-Alder reaction. It's just that the product is now something that has, whoops, I put those chlorines in the wrong spot. What am I doing? It's something that has 2 double bonds instead of 1 double bond in the product. We follow the same stereochemical model for the carbons that aren't double bonded in the final product. But you can see it doesn't complicate our lives too much because all we have to do is add an additional double bond. So we soaked up one of the double bonds when we made a new sigma bond, but we still had to leave the other double bond behind. We had to leave the other pi bond behind. Okay. There's some fun examples of this. Like you could consider a system like this. This is a really cool diene because it's fixed in the S-cis conformation. And then we could have that reacting with our alkyne. And when this undergoes a Diels-Alder reaction, you actually form a benzene ring. We'll talk about how important benzene rings are in the next unit. Okay. Now, with this double bond, I'm officially done with the Diels-Alder unit. A lot more to say, but I'll save the rest, or I'll omit the rest. Okay. All right. Good luck studying. Hopefully you enjoyed it.